On March 11, 2011, at 2:46 p.m. local time, the Earth beneath the Pacific Ocean shifted violently. Off the northeast coast of Japan, a magnitude 9.1 earthquake tore open the seabed and unleashed one of the most powerful and devastating tsunamis in recorded history. Towering walls of water swept across cities and villages, leaving more than 18,000 people dead, countless homes destroyed, and causing the Fukushima nuclear disaster. Yet for scientists, one of the most shocking revelations was not just the human tragedy or the scale of destruction. It was the location of the fault rupture. Instead of happening deep underground, where scientists had always expected such violent slips to occur, the rupture happened right at the shallowest edge of the fault, just beneath the seafloor. More than 50 meters of slip tore through this zone, displacing unimaginable volumes of water and triggering the catastrophic tsunami. This discovery challenged decades of geological theory and raised urgent new questions. Why did the fault behave this way? Could it happen again? And if so, where? In 2024, a group of 60 scientists from around the world set out to answer these questions with one of the most ambitious projects in earthquake science. They joined Expedition 405 of the International Ocean Discovery Program, also known as J-TRACK, tracking tsunami-genic slip across the Japan Trench. Their goal was to drill deep beneath the seafloor into the exact fault zone that ruptured in 2011 and recover direct samples of the rocks and sediments that had once unleashed a disaster. The mission took place aboard the Chikyu, the world's largest and most advanced scientific drilling ship, equipped with technology capable of reaching extraordinary depths beneath the ocean floor. For 4 continuous months, from September to December, the crew worked around the clock in one of the most dangerous regions of Earth's crust. The Japan Trench, where the Pacific Plate dives beneath the Okhotsk Plate, is a vast and hostile environment. The trench floor lies about 7 kilometers below the ocean's surface, a place of crushing pressures and complete darkness. It is here that some of the world's most destructive earthquakes are born. Normally, scientists expect the deepest parts of subduction zones to be responsible for mega-earthquakes. But the Tōhoku event in 2011 overturned that expectation, showing that the shallowest section of the fault, once thought to be relatively harmless, could instead produce catastrophic slip and tsunamis. This is why Expedition 405 was so important: to investigate the conditions inside the shallow fault itself, and to understand why it gave way so suddenly and so violently. Every 3 hours, as the drill penetrated deeper into the seabed, a new sediment core was brought up on deck. These cores were long, cylindrical archives of geological memory, each one holding a story written over millions of years. Scientists examined them immediately, shining flashlights through the transparent liners, looking for sand layers, volcanic ash, or anything that might hint at past geological upheavals. Once split open, the cores revealed stunning layers of rock and sediment. Some were faulted and fractured, evidence of immense tectonic stresses. Others displayed colorful bands of clay, with rich tones of chocolate, caramel, and cream, natural artistry born from Earth's hidden processes. One of the most important discoveries was the presence of smectite, a type of clay mineral. Smectite is known for its slippery properties. It reduces friction when wet, acting like a lubricant inside faults. This could explain how the shallow section of the Japan Trench Fault was able to slide so easily during the 2011 earthquake. Instead of locking up and building strain like deeper rocks, this clay-rich zone may have allowed sudden, massive movement, making the earthquake even more destructive and generating the giant tsunami. The cores also revealed deposits known as homogenite turbidite sequences. These form when a powerful earthquake shakes the seabed, triggering underwater landslides that send downflows of sediment, followed by the slow settling of particles stirred up by the tsunami. Each sequence acts as a geological time capsule, recording past earthquakes and tsunamis in layers that can be read like pages of a book. By analyzing them, scientists hope to reconstruct a long-term history of mega-earthquakes along the Japan Trench, stretching far beyond written human records. The deepest point of the drilling mission reached the décollement, the basal detachment zone where the Pacific Plate begins its descent beneath Japan. This is the very plain that ruptured in 2011. Here, the team recovered chert, a hard, glassy rock, marking the boundary between deep-sea sediments and the oceanic crust. It was in this critical zone that the violent slip of the Tōhoku quake originated. For the scientists on board, reaching this point was like touching the scar of a wound that had once shaken the world. But the mission was not only about recovering samples. The team also installed a long-term borehole observatory within the fault itself. This advanced system of sensors was designed to record real-time data on temperature changes, fluid pressures, and subtle movements within the rocks. Such data may reveal the hidden processes that precede an earthquake, tiny shifts, chemical signals, or thermal patterns invisible at the surface. For the first time, humanity now has a stethoscope pressed directly against the heart of a megathrust fault. The significance of this work extends far beyond Japan. Subduction zones exist all over the world, off the coasts of Chile, Alaska, Indonesia, and the Pacific Northwest of North America. Many of these regions lie close to major cities and dense populations. If shallow slip can occur in Japan, it could also occur in these other subduction zones, creating devastating tsunamis in places like Santiago, Anchorage, Jakarta, or Seattle. Current hazard models, which often assume shallow faults are less dangerous, may be dangerously incomplete. The discoveries from Expedition 405 could reshape how we assess risk, prepare evacuation plans, and design early warning systems worldwide. For scientists, the drilling mission is not just a triumph of engineering and collaboration. It is also a race against time. Earthquakes are inevitable. We cannot stop them. But by studying the conditions of the faults that generate them, we can better understand how often they occur, how powerful they can be, and what signs may appear before disaster strikes. Every core, every measurement, every sample taken from beneath the Japan Trench is a piece of knowledge that brings us closer to resilience. The 2011 Tōhoku earthquake and tsunami left scars that will never fully heal. But from that tragedy has come a new determination: to uncover the hidden forces that shape our planet and to prepare for the next event, wherever it may strike. The mission into the Japan Trench represents one of humanity's most profound efforts to understand the Earth's most violent processes. By unlocking the secrets of the shallow fault, scientists are building not only a record of the past, but also a shield for the future.